a little analogy that I made to try to help us understand this quantum level a little bit better. Because the tricky thing about it and why it's hard is the quantum level gets really, really, really small. And so it's hard for us to sometimes grasp our minds around it. Now, the analogy is just there to help you. If you don't like it, that's fine. You don't have to use it. But hopefully for some of you it will help. Okay, so what I'd like you to do is, so we have that note page from last time, right? That we filled out separately. On the back of that, because it's blank, we're going to draw my analogy picture. But then we'll also be in the note packet as well, filling out some definitions. So if you want to have like both of them there, kind of side by side, kind of pull out the last time's paper just on the back, and then your note packet. Honestly, you could write it anywhere that's blank too, but that's just kind of where we found was a good place to put it. So what we're learning today, like I said, are these quantum numbers. There's 4 of them we're going to learn about, and you can kind of relate it to like an address for the electrons. So when you give someone your address,
I'm not giving you my address.
Oh, dang.
Are you done with the white tubes today?
Yeah, I'm ready.
I just put it in the room. I'll be fine.
Yep. Yep, because this was the last class I needed, so. So with an address, right, like when someone says, what's your address? You tell them your house number, your street number, your city, and then the state. Right, that's your full address. So in a sense, there's 4 things that designate where you live. That's the same thing with our 4 quantum numbers. We're just going to do it kind of in reverse where we get more specific as we go down. Now the analogy that I come up with is we're going to pretend that an atom is like a hotel that the electrons are staying in. Okay, so our little atom here is a hotel and the electrons are coming to check into the hotel, and we need to be able to tell them where to go. Okay, so we're going to draw a picture of our hotel. So I'm going to draw it right here. So this is what you're going to draw on your blank paper. It's going to be, so if you want to kind of map it out, I'm starting down and I'm building up, and I'm building this way. So I would start like in the bottom left corner of your paper. Does that make sense? Some people started other places and then they got frustrated because they ran out of room. Okay, so here's the ground of our hotel. Okay, now technically when we're talking about electrons, where are the electrons in an atom? Good, outside the nucleus on our rings, our energy levels, right? So technically the basement of our hotel is like the nucleus, because the electrons don't ever go there, okay? Now, what we're going to talk about first, the first quantum number when an electron comes to check into the hotel, is we need to tell them what floor of the hotel to go to. Okay, so the first quantum number is analogous to the floors of our hotel. There's like my little key off to the side. You're like at the tippy top of your page. You should be fine there. Okay, so on the first floor of our hotel, there's only 1 room. So draw a little box. Okay, the first floor of our hotel only has 1 room. The second floor, and so let me preface this too, all atom hotels are built the same. So if it's the hydrogen hotel or the silver hotel, they're built the same. The only difference is how many occupants they have. Hydrogen only has 1 electron in its hotel, while silver has like 47 in its hotel. Okay? All right, the second floor of all hotels has a room that's the same size as the one right below it. And then it has a second room that's a little bit bigger. And that's it for the second floor. So second floor only ever has 2 rooms. The third floor of our hotel has 3 rooms. The first 2 rooms are the same size as the ones below. But the third room on the third floor gets a little bit bigger. Now, yes, this hotel is defying gravity. Okay? All right, now, anyone notice a pattern? So the first floor has 1 room, the second floor has 2 rooms, the third floor has 3 rooms. How many do you think the fourth one has? 4 rooms. The fourth floor has 4 rooms. There are a lot of patterns, and the more you can recognize them, the simpler this will all become. So the fourth floor has 4 rooms. And the fourth room is bigger than all the rest. Now, we're going to stop building for now. Let's connect it to what an atom is. So the first quantum number in an atom is known as the principal quantum number. The symbol that we use to designate the principal quantum number is the letter N. So the letter N signifies this principal quantum number. It tells us the energy level that the electron is on. So coming back to our hotel, this would mean N equals 1 would be the first floor, N equals 2, N equals 3, N equals 4, so on and so forth. Now for smiley face, don't shout it out loud, but think in your head. For my analogy, if this is a hotel, it's that hotel, raise your hand if you have an idea of how is it possible that the fourth one has so many more rooms compared to the first one. What about an atom prevents the first floor from having more rooms? So raise your hand if you have an idea of how that connects to our picture. So make a connection between this and this of why can the fourth floor have more than the first one? Mary, why do you think?
It's kind of like how those have the first ring and only have 2.
Perfect, right? It's because we're dealing, she goes like this, it's a circle, right? And so the first floor is smaller than the rest. There's no room for more than 2 electrons, so there's only 1 room for them to stay in. Very good, Mary. Have 2 smiley faces for that. If you were thinking what Mary's thinking, you can also have 1 smiley face. So this also tells us how big the atom is. The more energy levels that are filled, the bigger it gets. Right? So obviously the 3 is bigger than the 2, which is bigger than the 1. Now, the scientists do not know how big the hotel could get. So technically it ranges from 1 to infinity. The biggest ones we have right now go up to 7. But if we make a new element, we'd actually be moving up to 8 for the first time. And they don't know if there is a limit to where it stops. The cool thing about this, and I'll show you the connection in a second, is we can find this quantum number on the periodic table by counting the rows. So by counting downward, you can figure out what level of the hotel that atom would be on. And I'll show you this here in a second. But the biggest thing that we're going to see is that each block gets numbered separately. So each block is numbered separately. We'll come into this here in a second. Okay, coming back to our picture here. So the first one, we have our first quantum number, the floors. In terms of our analogy, are equivalent to the energy levels. Okay? So when an electron comes to check in, ding, I'd like to check into your hotel, the first thing we tell them, okay, go to the 3rd floor. What would be the next thing we would need to tell them? Good, which room they need to go to. Okay, so the second quantum number deals with the room that the electron is going to. Now, each room in the hotel has a specific label, right? Kind of like how they do in most hotels, right? Like you can get like a room with a king-size bed, you can get like a suite, you get the really simple one. So these all have special designations. So all rooms that are of this size are labeled as the S rooms. Okay? All the rooms that are of this size are labeled as the P rooms. These ones are called the D rooms. And then the biggest ones are called the F rooms.
Hey,
They're so fun.
Spectroscopes. Do you still have them?
I thought I put them in there. Oh, check on, I can't just move them on the ground. Okay. Because Rachel's sub was coming in. Now, each of these different types of rooms correspond to the blocks on the periodic table. And you should already have a picture in your note packet where this is like labeled with S, P, D, and F. Right? So we don't need to label that in. Okay? So by name, this second quantum number is known as the azimuthal, or the angular momentum quantum number. It's a little bit of a mouthful. Its symbol is a letter L. By the way, that's not a 1, that's an L. So L is what we use for the second quantum number. What this tells us is it tells us the energy sub-level. The energy sub-level, and it also helps us know the shape of it. Are you done? That was so fast. Thanks. Do you want to take...
Just have him look for him and then...
Can't find him? Okay, I'll check. Maybe her sub put him somewhere weird. I'll take a look.
It's okay, we can do it without it.
Okay. Okay, give me 1 second, guys, to go find the spectroscopes. Maybe that's what we feel it. So do you see your picture that has these shapes on your notes? Next to those shapes, write these designations. So this shape is L equals 0, this one is L equals 1. So label those on. Okay. Okay, sorry about that. We'll have to edit that out of the video. Okay, so the second quantum number, everybody. Okay, phones should be put away. Okay, this is hard enough to learn as is. Don't make it harder on yourself by missing pieces. Okay. The second quantum number tells us the shape. Now, this is a little bit crazy to try to comprehend, but do your best to visualize it. Okay. So an s orbital looks like this in terms of the pattern that it orbits. So when an electron is in an s orbital, or I guess I should say s sub-level, it orbits in a spherical shape. But if it's in a p sub-level, it orbits in that shape. If it's in a d sub-level, then it's orbiting like so. And then f gets a little nuts, right? Now, look at the fourth floor, right? So on the fourth, so this one doesn't have four, but imagine there's 4 rings on this. The ring is simply the energy level. That's all the model shows. Past that ring are sublevels, or inside of it are sublevels. And on the fourth one, there's all 4 of them. So take all 4 pictures and overlay them on top, and that's just the 4th energy level. Underneath that is the 3rd, and then underneath that's the 2nd, and so on and so forth. Right? So there's a lot that's going on as we dive deeper into an atom. Okay? So our second quantum number, I guess let's write right here on our key, where my pink one go. This designates the sublevel. Now, this isn't on your notes, but it's something you will be doing on your homework, is you should be able to tell from looking at the periodic table the first 2 quantum numbers, because it's like a map. Now, the other quantum numbers we'll talk about, you can't do on here. You need more than the periodic table shows us. Okay, so I'm going to do the first one for you, and then I'm going to have you try some others for a smiley face. So we're trying to find the 2 quantum numbers for barium. Now, barium's technically here, not there. So just move the 5 over slightly. Okay? So the first thing that we do is to find the first quantum number is we count down from the top. But you have to count down differently for each group. Since it's in, what section is this for letter? Good, so we're in the S section. Where do the S rooms start? Where's the first S room in our hotel? On the first floor, right? So for this column of yellow, we start counting at 1. So I just go over the top, 1, 2, 3, 4, 5, 6. So the quantum numbers for this would be 6S. Now you could also say 6, 0, because that's what we just labeled, right? That S is 0. But we'll use the letters way more than the numbers, so I encourage you just to use the letters. Okay? All right, I'm going to do number 7 with you, and then I'm going to try another one. So coming over to 7, so which section am I in? Good, so this is a P block, so I know it's in a P-type room. Now we have to count down, but here's the difference, is what floor do the P rooms start at? The 2nd floor. So don't start counting at 1. This is 2. So 2, 3, 4, 5. So we would say the answer for this would be 5P. Okay, for a smiley face, let's just jump into the water. You can talk to your table if you want. What are the 2 quantum numbers for number 6? So figure that out. Take a logical guess. Okay, show me on your fingers what is our first quantum number. So just show me the first one. So not the letter, but the number. Even if you think you're wrong, please show me, because it will show me that you need help. If you're not showing me a number at all, then I don't even know if, like, are you just not paying attention? Are you being rebellious? Like, what's the deal? Okay, so show me something even if it's wrong. Okay, very good. So how do I know it's 3? Emily?
Because you're in the D block and the D room start at.
Good. So we're in the D. It's on the first row, but D doesn't start until 3. So this is 3D is the final answer. Good. If you got that, have a smiley face. Okay, let's try number 8. So figure out number 8 with your table, buddy. What would be the 2 quantum numbers for this one?
Wait, so like the top line is the starting number?
Yeah, so the top row is where you start counting from. The question is just where are we starting from, right? Like which number? Okay, in the count of 3, shout out your answer. Ready? 1, 2, 3.
5F.
Good job. If you said 5F, you're correct. That's my face. Well done. Questions on that? Now you should notice that you have this diagram in your note packet, like so, and this shows you and how it counts. But I encourage you not just to try to memorize this massive thing, right? Just recognize where each one starts and notice the pattern. S starts at 1, P starts at 2, D starts at 3, and F starts at 4. And then you just count down from there. Yeah, Alex. Yes, if you notice on this other picture we had, when we talk about blocks, we often put helium over here. Yeah, no, good observation. So it is part of the S block. The reason why it's over there on the periodic table is because that is its family. But in terms of our electrons, it's part of the S. So good observation. Okay, now we're going to tell the electron, okay, you're going to go to this floor, you're going to go to this room. So there's our first 2 quantum numbers. Now the third thing, because this hotel is really special that we're going to tell them, is our hotel has bunk beds. Who doesn't love bunk beds? Okay. Now each type of room has a special designation of how many bunk beds it can hold because of its size. So all of our S rooms only can hold 1 bunk bed. That's a bunk bed. Okay, so I'm not going to draw them in all because that just will take too much time. But all of the S's have just 1 bunk bed. Okay? All of the P rooms will have 3 bunk beds. The D rooms have 5 bunk beds. Anyone notice the pattern?
1, 3, 5, 10.
7, good. 1, 3, 5, 7. Okay? And all of those types of rooms, so all the P rooms will have 3. The P room, that's as many as you can have. Okay? Now, before we talk about the name of this quantum number, I want you to see, so don't say it out loud, but raise your hand if you see a connection between the periodic table and the number of bunk beds in each room. And there's a very particular reason why I picked bunk beds for my analogy. So look and see if you can find a connection between the number of bunk beds and the periodic table. Raise your hand if you have an idea. Anders, what do you think?
This is going to be kind of hard to explain.
You're okay.
So the S block has 1 bunk bed,
Uh-huh.
and so technically there's 2 beds, and so then there's like two, yeah.
Good.
So that's for all of them.
Yes, very good. Anders, have 3 smiley faces. So same thing. Notice that P has 3 bunk beds. So how many can sleep in there? 6. 1, 2, 3, 4, 5, 6. So technically, you don't once again even have to memorize how many they have. If you ever forget, like, how many bunk beds are in a D? Just count. And that's how many electrons, so then cut it in half, and that's your number of bunk beds. Okay? The bunk beds in a real atom correspond to what we call as orbitals. So we're getting really deep here, okay? So we have the energy levels. Inside this energy level is a sublevel. Inside that sublevel are orbitals. Okay?
We're going to do which side of the bed is.
Very good. Cam sees where we're going. So our third quantum number is known as the magnetic quantum number. Its symbol is an M with a little subscript of L. It helps us understand the orientation of our orbitals. Because atoms are in 3D space, and so a P can be oriented different ways. So the 3 orientations of the P correspond to the 3 different bunk beds. Each bunk bed represents a different orientation that it can do. Now, this one got crossed off by your picture, so add this on here. The range for this quantum number, okay, this quantum number ranges from negative L to positive L. So those are the possible values for this quantum number. Now, we won't be dealing with the calculations of these quantum numbers. That's past the scope of this class. But that kind of just helps you get the understanding of the math if we were going to get into that. Okay, so our 4th quantum number, I'm going to tell the electron, okay, go to the 3rd floor, go to the P room, go to the 2nd bunk bed, and now we have to tell them if they're sleeping on the top bunk or on the bottom bunk. Okay? This 4th quantum number corresponds to the spin of the electrons. So when 2 electrons are in an orbital together, they will always spin in opposite directions. The numbers that we classify them as is a +1/2 for up spinning and a -1/2 for down spin. The biggest thing about these orbitals, though, is they can only hold 2 electrons. That's why it's a bunk bed, because one is on top, one's on bottom. And they must always be opposite. Okay, 2 electrons will never share the top bunk. They'll never share the bottom bunk. They all want their own because they're negative. Right? They don't want to share. Okay? Now, so once again, the top or bottom corresponds to the spin of the electrons. Now, what we mean by spinning here is you have to recognize that so the electron is orbiting around the nucleus in whatever pattern, right, it's supposed to be doing. But just like the Earth orbits the sun, the Earth is also spinning, right, because that's how we have night and day. So that's what the electrons do as well, is they're spinning like a top while they're orbiting around the nucleus, okay? And they're always spinning in opposite directions, okay? Now, these 4 quantum numbers is what we'll put together next time and see how we can designate where the electrons are or how to write out the address. The one other piece that we still need to talk about, and here's the introduction to it. Oh, first off, I guess, both the spins are worth the same amount of energy. So it's not more energy to spin up or down, it's the same energy. Next time what we'll get into more are the rules of our hotel. So when an electron comes to our hotel, there are a set of rules that we follow to put them in the hotel. The first rule is known as Pauli's exclusion principle, and this rule says no 2 electrons can have the same 4 quantum numbers. Meaning they can't be on the same floor, in the same room, on the same bunk bed, and both be on the top. That breaks the Pauli's rule. Now they could be on the same floor, in the same room, on the same bunk bed. So the first 3 can be the same as long as one is on top and one is on the bottom. Okay, so no 2 can have the same 4 quantum numbers. Because the last quantum number signifies which electron it is.